Deformable linear objects, shortly DLOs, are a class of deformable objects consisting of cables, wires, ropes, tubes, and many more. These objects are vastly present in our everyday life and in industries. However, very few robotic systems are currently deployed in scenarios in which a proper perception of DLO is required. This is due to the lack of a stable, efficient, and accurate approach for their perception. We propose a novel approach that is able to perform a reliable and efficient instance segmentation of DLO from images. We deploy synthetic data for the learning methods and a similarity network for solving the DLO intersections. The proposed method shows stronger performances both in terms of accuracy and inference time against the existing methods. The proposed method takes as input an RGB image and provides as output a mask where each DLO is denoted with a unique color. In addition, each DLO instance is interpolated in image space with a spline curve. We deploy a DCNN for the segmentation of the background, where a synthetic dataset made in Blender is used for its optimization. The background segmentation is accomplished as a semantic segmentation task consisting of just one class, that is the DLO class. So the output of the DCNN is just a binary mask. On the obtained binary mask, a skeletonization approach is performed as shown in the example images. Each pixel of the skeleton is classified in one of these three classes. Indeed, if we slide a 3 by 3 kernel on a target pixel, we can end up only with 1, 2, or 3 other skeleton pixels locally. This is a result of the skeleton structure being connected, but only 1 pixel thick. The intersection pixels are discarded from the skeleton mask since they correspond to a topologically misleading area due to the DLO crossing. From the updated skeleton mask, new endpoints are extracted. Thus, segments are generated between 2 connected endpoints. With segment, we denote an ordered sequence of section pixels with endpoints at the extremities. Employing the skeleton mask, for each segment an overall thickness is estimated that is going to be used as one of the features of the similarity network. The similarity network is employed for processing the intersections. The feature vectors of the endpoints of 2 candidate segments are compared via a shallow neural network, and the probability of their connection is predicted. The similarity network takes as input the source image and the binary mask, along with the endpoints to test. The feature vectors are thus computed integrating the segment's thickness and endpoints' local colors and directions. The connection probability between endpoints is obtained by computing the distance of the embeddings followed by a Gaussian activation function. An example of the similarity network output is provided at the bottom of the slide. Exploiting the endpoint pairs predictions, it is possible to concatenate the associated segments, reconstructing the full description of each DLO. The concatenation is performed sorting the connection probabilities in descending order, thus prioritizing the best matches. Once the single DLO are obtained, their relative ordering or layout at the crossing is estimated from the RGB image. In particular, the mean standard deviation of the RGB values along the line connecting the merged segments is computed. The DLO with the smaller estimate is placed at the top. The experiments focus on the method accuracy and inference time. A dataset of 135 manually annotated real images of electric wires is used for evaluating the method accuracy and provide comparisons. The test dataset comprises DLO of varying diameters and scenes with 1 to 3 intersecting DLOs. The baseline methods are both DLO-specific and general-purpose network models. Overall, the proposed method shows better performances surpassing the current state-of-the-art method. The improvements can be also qualitatively appreciated in the images on the slide. The method is tested with different backbones for the semantic segmentation network and different number of DLO intersections in the scene. The results are provided in the table. A processing time between 40 and 50 milliseconds is experienced across the entire dataset, with an average of 45 milliseconds and a frame rate always higher than 20 FPS. The hardware specifications are available at the bottom of the slide and in the paper as well. The method in action is shown in this slide. The different backgrounds cone, C2, and C3 are the same employed in the experimental part. The source code of the proposed method is freely available at the link of the slide and in the video description. Feel free to try it out. Thank you.